Alright, you guys, let's explain why momentum is conserved for two or more objects exploding apart. Okay, so when we're talking about multiple objects, we're now talking about a system of objects. So here I'm going to draw a big square around my system of objects. We have a blue and a red cart with force sensors on them, so we'll be measuring the force. And we're going to collide these into each other. So we're going to send this guy, we're going to send this guy to the right, and we're going to send this guy to the left. And they collide with one another. And maybe they bounce off. I don't know. It doesn't matter. But let's just talk about this moment of while they're colliding. So when they collide, they produce a force versus time graph that looks like this. And you start to see a pattern here. You would notice very quickly that the area of this shape, which is a triangle, is going to equal the area of this shape. And if you remember what the area of a force versus time graph shows you, it shows you the change in momentum. So I know that the change in momentum that the blue car experiences, it's going to equal the change in momentum that the red car experiences, with this one key difference. The change in the momentum of the red car is negative. So the blue guy is positive, the red guy is negative, and they cancel out. So they sort of cancel each other out if you're thinking about the system as a whole. So the change in momentum for the system is zero. It doesn't change. And so that's the law of conservation of momentum. Momentum is conserved. So let's look at that again, just one by one. The change in momentum for each object is the same in magnitude, which means amount. So it's the same in amount, but opposite in direction. And the total change in momentum for the system of objects is zero. So there is no change. And that means that for the momentum for the system, there is no change. In other words, momentum is conserved. Now the word conserved, it means what you think it means. It means you're conserving something. You're holding it safe. You are, like you might have heard, the conservation of the environment. That means we're keeping the environment the same. We don't want to degrade it. We don't want to change it. We want to conserve it. So some synonyms might be keeping momentum, the change in momentum constant, or momentum constant, and the change would be zero. Or, the same. That's what we mean when we say conserved. And I think it makes sense to most of us, especially if you understand this graph and you know that the area of the graph is the change in momentum. You might remember that the area of the graph is the impulse, but if you remember the impulse change in momentum theorem, you'd know that the impulse and the change in momentum are the same thing. So that's a little side note there. Hashtag facts. The law of conservation of momentum. The law of and these guys, I would turn these into flashcards. Because these are some key ingredients. The law of conservation of momentum states that the total momentum of a system before a collision will equal the total momentum of a system after a collision. So let's underline before and let's underline after, just so we know that we're talking about initial conditions and final conditions. It's a way to gear our heads, but when we're thinking before and after, we're thinking about changes. The momentum for an individual object does not change. Oh, I messed up. The momentum for an individual object does change in a collision. It absolutely does. I mean, look at this blue car. It started out moving to the left, collided with the red car, and then maybe it was moving to the right. That thing underwent a big change in momentum. It changed its entire directions. It didn't even slow down. It slowed down to a stop and then bounced back in the other direction. So, of course, you can see the change in momentum of the blue car. It equals this much. So individual objects, they do experience a change in momentum. But the total momentum for a system does not change, and that's the key. So, why do we care? Here's a pool table, and each one of these billiard balls, they are headed towards one another, or they're maybe going to bounce off. And if you knew something about the mass and velocity, if you knew something about the momentum of all of these objects before the collision, mv, the momentum of those objects before the collision, then you could predict, you could start saying, I know how these are going to behave in a collision, and I know what direction they're going to be moving after they collide with one another, and so I can start making predictions as a scientist or as an expert pool player. Here we have two galaxies colliding, and scientists are amazing in their ability to generate these models. I don't actually know if this is a perfect scientific model. This could just be sort of a particle effects simulator. However, each one of these galaxies are filled with billions of stars, billions and billions of stars, and these stars have a lot of mass and they're moving really fast. And if you knew something about the initial conditions, the before momentum of each one of those stars in these galaxies, then you could predict how these galaxies are going to behave in a collision. And then you can animate that by plugging in any formulas into your physics engine, like you would literally plug in the conservation of momentum. So I just think that's pretty cool. That's how scientists are able to make predictions. So the law of conservation of momentum allows scientists to make predictions. Now, why is momentum conserved? If you look at the learning objective title, explain why momentum is conserved. So you guys will need to be able to do this. Explain this that I'm about to explain now. So why is momentum conserved? Hint, it relates to someone's law. Can you guess it? So, somebody's law. Okay, so most of you guys are like, I know it's Newton. I know what you mean. It's Newton. You're talking about Newton. So which law is it? Is it first, is second, is third? Well, down here we have a force of the blue guy on the red guy. And we have the force of the red guy on the blue guy. It's an applied force. And when I say blue guy and red guy, I mean these carts when they hit each other. And can you guess it? And some people are thinking, I remember, for every action, there is an equal and opposite reaction. And that is Newton's bing, 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 Newton's third law. Every action, there's an equal and opposite reaction. That's how you remembered it in middle school, but I want you to remember it the high school way. And in high school, we say every force is a pair, where each force is equal in magnitude, but opposite in direction. That is Newton's third law. Third law. And the colliding objects, any two objects collide with one another, that's going to result in some force pair. That applied force on one another. So there is a force pair there. And here it is. There's my force pair. This is the positive force of the red on the blue guy, and here is the negative force of the blue guy on the red guy. So since the blank of the collision is the same for both objects, so not only is the force the same and equal and opposite, but look at this. Look at this piece of the puzzle here. This right here. The x-axis represents time. And these objects are interacting with one another, so of course the time that they collide with one another is going to be equal. It's going to be the same for each object. And so you can say since the time of the collision is the same for both objects, then the impulse exerted on each object is going to be equal and opposite. So we have the same. Let's look at the equation for impulse. If we have the same force that are the same amount of force, but opposite in direction, and we definitely have the same amount of time, then we have the same impulse. So let's just really quickly make that into like a logic statement. If the forces are equal and opposite, and the time is equal, then the impulse will be equal and opposite. Look at that perfect logic statement that this equation allows us. According to the now we got to make our jump. So we started at Newton's third law talking about force. We combined it by talking about time, and now we're talking about impulse, and now we got to make our jump to momentum. Because we're trying to prove the law. According to the law of conservation of momentum. According to the impulse change in momentum theorem, both objects will experience equal and opposite changes in momentum. So if they have equal and opposite impulses, then they will have equal and opposite changes in momentum according to the impulse change in momentum theorem. Beautiful, beautiful. So we started at Newton's third law talking about force. We looked at those graphs. We noticed that the time of collision was going to be the same. We reasoned that because the force and the time were the same, the impulse would be the same. And because of the impulse change momentum theorem, we also know that their change in momentum is equal and opposite for each object. So, for example, if one object... Right here, I'm done here. For example, if one object experiences a change in momentum of 50 kilograms meters per second, the other object will experience a change in momentum of... I'm waiting for you guys to write it ahead of me, because I bet you know. Okay, fine, we'll write it together. Negative 50 kilograms meters per second. So if one object in a collision experiences a change in momentum of 50 kilograms meters per second, the other object will experience a change in momentum of negative 50 kilograms meters per second. And for the system as a whole, there will be no net change. So if you take the sum or if you add them up together, there's going to be no change. So let's review. The law of conservation of momentum states that the total momentum of a system before a collision will equal the total of momentum of a system after the collision. After the collision. Cool beans, everybody. You've made it through. This is one of the most difficult things for you to reason, but without this document, if I were to ask you, why is momentum conserved? Could you explain this? Could you explain this? And if the answer is no, then I would suggest watching this part of the video again and practicing doing exactly what I just did, starting at Newton's third law, talking about the time of collision and relating the fact that they have equal and opposite forces and the fact that they have the same amount of time, then they must have the same impulse. And if they have the same impulse, then equal and opposite impulses, then they must have equal and opposite changes in momentum. And then so the changes in momentum for each object will cancel out so that the system as a whole, there is no net change. So that's what I'm hoping that you will be able to do, is explain why momentum is conserved. And I know that you can do it. I believe in you. Good luck, young physics geniuses.